in the jump, and this is quantum gravity. See, in the moment in which Dante is left alone by Virgil, it's alone, it's a moment of, he says, "Oh, Padre mio," my father, because he's of this respectful thing with this great poet of antiquity. He's scared, he's alone, he knows his own, but in that moment he sees Beatrice, which is his great love. Dante has been in love with this woman all through his life. And he sees there, and it's just joy, light, colors, fantastic. This is a beautiful moment of the poem. So there, in the moment of his light and desperation, and he finds his great love. For me, it's been the same. Going there, in the moment in which we lose Einstein theory, that's what quantum gravity is. It's what I've been looking all my life to. And I think the beauty and the hard part also to understand is this jump. Because this jump is not a movement of space or evolution in time. And it's not a jump of an electron from here to here, where space remains space, time remains time. It's just a funny electron that does funny thing. It's time itself and space itself a jump from one trajectory to another trajectory. So we have to conceive a way of thinking about physics where you can describe a phenomenon, a normal phenomenon of the universe, not as happening in space-time, but space-time itself does something funny. That's So here's a picture. Here's a complete picture. Star collapses, black hole forms, becomes very long, and quantum jump, white hole, and slowly it comes out, everything comes out, and the entire process is finished. Now, first question, how long does it take? Okay, I think you're quite on board on the fact that how much time is a funny question here. It's a tricky question. How long does it take? If we're outside, it might take very long. In fact, it might take extremely long. When we started doing these calculations of the quantum jump, because the classical part is just Einstein equation, it's just technical. We use quantum gravity to the calculation. We realized that the probability jumps happen with certain probability. Quantum mechanics about probabilities. The probability for jump to happen, seen from the outside, is completely negligible if the black hole is big. It's only possible if the black hole, if the horizon is small. Now this seems to a big problem because, oh my God, but most black holes we see in the sky, they're big. They're not gonna never happen there. But black holes become smaller with time. That's a big discovery of Stephen Hawking, that black holes evaporate. If you keep feeding it, it becomes bigger. But if at some point they eat whatever there is to eat, at some point they're isolated and slowly they emit energy and they become smaller and smaller and smaller and smaller. So if you wait long enough, even Sagittarius A star, which is this gigantic black hole, even the biggest one, the billion solar masses black hole are going to shrink, 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 and become very small. Once they're small, the probability of jumping is very high. In fact, it becomes order 1, and it jumps. So the correct story, cosmologically or astrophysically, the likely story is that whatever black hole you have, it's going to take some time, and the time was computed by Hawking, to become small, then it jumps, and then becomes a white hole. The white hole is teeny, 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 because it's at the end of evaporation, but careful, it's teeny, the bottleneck. The inside is big, and takes a long time to come out the inside. So that's the full story. Now, question is, how long does it take? Well, a black hole, you have to wait for it to become small. And this was computed by Hawkins. It's for a black hole of the size of Sagittarius, it takes much longer than the life of the universe. Long, 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 long. Okay? So this happens, and then so billions and billions of years. But remember, I said we went inside the black hole, we go through these things, we're in the white hole. The time it takes in Sagittarius A star from the moment we cross the horizon, for us, For us, we're inside the starship, we're going down. Again, assuming that we're not squeezed and squashed. Okay, we have a super powerful kryptonite starship that is going through all quantum jumps of the time it takes for us to go to the jump is minutes for a big black hole. For a small black hole, it's seconds, even less. The jump is instantaneous, and the time to get out from the white hole is very short, again, minutes. So outside, the time is billions of years. Inside is just seconds or minutes. Okay? Which means that the full process is something that lasts billions of years for a clock outside, minutes for a clock inside. Which means if you want to see what is the universe billions of years in the future, just jump to black hole and you get it in a moment. Again, assuming you're not squeezed, squashed, and destroyed. So, one way of viewing what a black white hole is considering it as a shortcut to the future. You just go in, boop, you come out in the future. There, in the same place. Okay, you just hole, go in, and bloop, you come out from the same hole, long away in the future. That's this enormous time distortion. It's the same kind of time distortion of my clock, except that it's gigantic, right? Another way of thinking about that is to think that what is really going on is that you have a star, it goes down, collapses, bounces, comes up, but because of time distortion, you're seeing this at a slow motion. Unbelievable slow motion. For billions of years, just wait. But it's you who are seeing it slow motion because of time dilation. So that's a picture the likely picture of what is going on. Now, one question is. Do we believe this? Can we check this? How can we check this? How do we hope to see if this is right or wrong? And as I often say, I've been working this for the last years. Sometimes I'm completely sure it's right. Usually on Mondays, I'm completely sure. Usually on Friday, I'm totally desperate. No, it's not going to work. How do we check this? If this is right, what could we do to find out it's correct? One thing is that we might see some indirect effect of that, and once we could actually see these things directly. So the indirect effect. In fact, let me make a small parenthesis about black holes. Black holes, the first evidence, the first time astronomers could see something in the star and they thought, well, that's maybe a black hole, was in the 70s. But it was just a few astronomers, nobody was taking them seriously. There were some stars that were wiggling. We could see the Doppler effect, they're moving back and forth, like if we're rotating around something, but there was nothing around which to rotate. And somebody says, maybe it's a double star, and one of the two is a black hole. John Wheeler had a beautiful image. If you have John Wheeler is another generation, a couple dancing the waltzer, and he's dressed in black and she's dressed in white, and it's very dim. You only see her moving around like that. But you know there should be somebody else because she's... so that's the white dressed girl is the star that you see, the black is the black hole. That was the 70s, and still in the 80s nobody would believe black holes. It's only really this century that people, the scientific community at large, started taking the idea that black holes are real seriously. I say in the book that when I moved from America back to Europe, the director of my department in France, who was not a relativist, was a particle physicist, in 2000, told me, you don't really believe black holes exist. So still in 2000, many very serious, very good scientist wouldn't take this seriously. Now, of course, he changed his mind, but that's not a criticism of him, not at all, because changing mind is what science is about. I mean, that's exactly the best of science. Now, why I'm saying all this? Because in the 30s, much before, this guy constructed this antenna because he was working for the Bell Laboratory for studying noise in communications, and he picked up a signal from a point in the star, in the sky, which was in the center of the Sagittarius galaxy, in the center constellation, and was called at the time Sagittarius A star. He was seeing the black hole. Okay, the signal, the radio signal of the black hole, was received for the first time on Earth by somebody in the 30s, much before anybody even thought that that could be a black hole. It took half a century to recognize that that was a black hole. So it is not totally impossible that white holes is something we have already seen. And in fact, imagine that in the early universe, we know the early universe was very hot and very agitated, and there's a lot of speculations that in the early universe a lot of black holes could be formed at the time. They're called primordial black holes. Or imagine even there's a lot of speculations that Big Bang was not a beginning. There was a big bounce, so a previous universe compressing and bouncing. And in fact, the bounce of the universe is a phenomenon which is sort of vaguely similar to the bounce of black hole that becomes white hole. So imagine that in either before or in the early universe many black holes formed, these have already become white holes. Now, small white holes, because as I said, the transition happens only when they're small. So imagine there are a lot of these small white holes, and the mass we can compute it. The mass, the theory gives it, it's a Planck mass, is a fraction of microgram, which is the weight of my hair. So 1 hair, 2 hair, that's a Planck mass. So a white hole is something which has the weight of this, much smaller than my hair, but has the weight of that, which means it's a gravitational attraction like this, teeny, which you couldn't see it because it doesn't interact electromagnetically. You could not touch it because touch it is electromagnetism, but you could, in principle, see it's a gravitational force. So imagine there was many of these teeny things in the universe formed in the past and were floating around. They would behave like matter because attractions have gravity, but they would be dark because they don't interact with light. So they would be dark matter. Dark matter? Astronomers see around galaxies halos of something that they call dark matter, which only interact gravitationally, doesn't interact electromagnetically, and behaves exactly as if it was many little teeny things with a Planck mass moving around. So could it be, and this is not something we know, it's a speculation, it's a possibility, could it be that perhaps we've already seen these things? These zillions of little white holes, which are ancient black holes that have bounced, and now are these teeny things, and they're detected by the astronomers, and that's what they call dark matter, which nobody knows what it is. It's one of the greatest mysteries of contemporary astronomy and science, that in the universe we see stars, we see galaxies, but then we have clear evidence, very strong evidence that there is something else, because we see its gravitational effect. These clouds, big clouds around galaxies, larger than the galaxy, of this sort of powder that only interact gravitationally. Okay, so maybe we've seen then, how do we get convinced that this is the case? That's the way science works, slowly in a complicated manner. We have to make a model that how they were formed before the universe, in the early universe, how had they interact with the full story of the universe, cosmology, and so on and so forth. Are there alternatives for dark matter? One alternative until short ago was supersymmetric particles, but that was wrong because supersymmetric particles don't exist of that kind, that particular kind that was expected. One of the